Okay, so this is the third video clip out of 3. This is looking at the impedance of a series circuit consisting of resistance, inductance and capacitance. So we're now talking about the quantities of resistance, reactance and reactance. So inductive reactance and capacitive reactance. Quick reminder, which is crucial to this phase, these two, the inductor and the capacitor, and their reactances are absolute opposites at any point in time in the circuit. So let's try and look at the impedance triangle. It's going to take this basic shape. Horizontally, always the resistor. What goes up the side? Well, it's reactance, but we've got two reactances, so it's quite simple. Just subtract one from the other. I've written XC minus XL. It doesn't matter. Just take whichever one is biggest and take the smaller one away. So I could have written XL minus XC. Then the answer to all of this is impedance Z. So that gives us the impedance formula, which must now reflect this. The impedance formula, Z equals the square root of R squared plus, and then we want this. So it's XL minus XC, doesn't matter which way around you write it, square that, and it's the square root of all of that. This is going to be in ohms. So this is now a crucial formula. Okay. So from that, let's now look at sketching out the phasor diagram. The phasor diagram must reflect the voltage across the resistor, the inductor, and the capacitor. Let's move to that now. So it's a series circuit. That means current is our reference. That's the first thing that we draw. We're then going to take each component one at a time. The resistor first of all. The relationship between voltage and current in a resistor is that they are in phase. There's the current. The voltage across the resistor is going to be there. If we then deal with the voltage across the inductor, the voltage across the inductor is going to go there. And the voltage across the capacitor is going to be down here. So here we see that the two voltages are 180 degrees apart. One is leading, one is lagging. So they have the effect of cancelling each other out. You literally subtract this from there. So we take away the smaller one from the bigger one. That's going to give us VL minus VC. VL minus VC. So we take the smaller one away from the big one. So I've now accounted for the voltage across each component, and I've reduced it to this red line. And if we do the dot to dot, then we've now formed our parallelogram, and that is the supply voltage. Phase angle always between the supply voltage and the supply current. Okay, so that's covered the basics. Let's move on and have a look at an example. So I've written out an example here. Very simple. A series AC circuit consists of a resistor of 75 ohms, an inductor of 0.6 Henry, capacitor 30 microfarads, supplied at 230 volts, 50 Hertz. Determine the circuit impedance, the circuit current, PD across each component, and sketch the phasor diagram. So we're going to go through all the same routines that we've done previously. Just at the end, the phasor diagram will look very slightly different. It's going to look similar to the example we've just referred to. So let's have a look at this calculation right now. The first thing we had to find was the impedance. So part A is the impedance. To find the impedance, we need to find XL. Put the numbers in. And that comes to 188.5 ohms. We also need to find XC. Value of the capacitor was 30 microfarads. Put that in the calculator and I'm hoping you're going to come out with 106.1. So now that we have the two x's, we can find z, which was what the question asked for. Square root of r squared plus XL minus XC squared. Put your numbers in. The resistor was 75, and then XL was 188, XC was 106. And if you put that in the calculator, we'll hopefully get 111 ohms. Okay, so we now have the individual reactances and we have the circuit impedance. With the circuit impedance, we can now find the circuit current. So I think this was part B. Current, I equals V over Z. Put the numbers in. The voltage was 230 and Z was 1.4. 2 and a bit, that comes to 2.06 amps. Okay, so before we can do the phasor diagram, we need to find the potential difference across each individual component. So, voltage across the resistor is I times R. 2.06 times 75 equals 154.5 volts. Voltage across the inductor. Voltage across the inductor is I times XL, 2.06 times 188.5 8.5 equals 388.3 volts. Next bit. Voltage across the capacitor. And we're back to the basic formula, I times XC, put the numbers in, 2.06 times 106.1, and that comes to 218.6 volts. So with all those voltages, we're now in a position to sketch the phasor diagram. So I'll try and squeeze it in down on this piece of paper. It's a series circuit, so current is our first phasor. The next bit, the voltage and current in a resistor, they're in phase. And we had, remember this is a sketch, but we had 154, so I'm going to do that. So this is 154.5, this is VR. Voltage across the inductor, that was 388.3, so that's going to be big. There we go. This is the voltage across the inductor, 388 basically. The voltage across the capacitor is the opposite, and the voltage across the capacitor was about 218. So your final step to finish this diagram off, we subtract the smaller one from the bigger one. So we're going to do VL minus VC. Put the numbers in your calculator, 388.3 minus 218.6. It's going to give us here 169.7. So that's going to be something like that. So this is VL minus VC. We now have the resistor voltage, which hasn't changed. The reactive voltages have reduced to the black one, and if we do that, then we can find the supply voltage. This is your phase angle phi.